My name is Peter Gould. I'm here to talk about serious science with open source tools. I'm actually here representing my non-serious job, my fun day job, which is Olympia Circuits. It's a little company my partner and I have put together to pursue some projects. And really what my talk's going to be about is melding my day job as a serious scientist with my fun job as a maker, and the potential I see there. And I think there's an enormous amount of potential for the maker community to contribute to the scientific community, and I would really like the scientific community to embrace some of the things that the maker community has developed. So my serious job, my day job, is a research scientist. I work in environmental science, forestry specifically. Some of the research I've been involved in is the effects of climate change on tree growth and how we can potentially mitigate some of the effects of climate change in the respect and how they might impact our forests. Some parts of this job include a lot of data collecting and including a lot of electronic data collecting. So in environmental science, we need to measure lots of things. And I'm involved in projects where we measure things from satellites, aircraft, embedded sensors, so from a big macro scale all the way down to a pretty fine micro scale. And I'll talk a little bit about some of the projects as I go. So really what this requires is an understanding of electronics and data logging, the ability to program, and a good background in statistics. So that's the serious science job. And then on the maker side, I've been involved particularly with Arduino, and I think most everyone knows what Arduino is. And if you happen to have successfully avoided learning what Arduino is at this point, I don't think you'll make it through the day without learning what Arduino is. So that's the other side, the maker side. Long-term interest in electronics and Arduino in particular. I think I went. So, okay. Just to give you a little background on one of my serious science jobs, this was a project looking at the effects of environment on tree growth, and we had some interesting tools here. We were using a commercial data logger on the upper left there. We were using a commercial sensor that actually wraps around the base of the tree, and it measures the growth of that tree every 30 minutes. So we get this pattern of growth over time. We have other environmental sensors on the data logger that look at things like temperature, soil moisture, humidity, and so on and so forth. It gives us the data we need to understand how environment affects tree growth and how future environments with climate change might affect tree growth. This is a great system. These things have been developed. They're out there. The problem is it costs about $1,200 for each tree. It's just very expensive to go through the commercial route. And it's not as much fun. It works. It just works out of the box. We need to do something that's more fun that we have to hack and build ourselves. Oops. I'll get this eventually. So there's a few reasons I see that scientists need makers, and then we need to interface the maker community and the scientific community. And I'm specifically coming from environmental science. And I think it's probably true with other sciences as well, but when I'm talking, I'm focusing a lot on environmental science. I think it's general science, and as a scientist, you have to do things that haven't been done before. So you don't go to the store and pick up the materials you need from Home Depot, although you can get some of them there. We have to have the ability to do new things. Otherwise, we're working within limitations. And I think to make progress in a lot of cases, we need to be able to do new things. We also need tools that haven't been invented yet. And we can often think of things, wouldn't it be great if we had this, and it didn't cost a lot of money, and we can put those out and measure a lot of stuff. Well, I think the maker community can contribute to that. In science, in environmental science in particular, you have to do a lot of measurements. You have to do a lot of replications. If you go out and measure one tree, you don't learn a lot. If you measure 100 trees, you learn a lot more, and it'd be even better to measure 1,000 trees. Gets back to this price thing. We need something that's scalable. We can do a lot of it. And not too much work to get it running. So on that front, we need to minimize costs. This is just keeping me busy. So we need to minimize costs, as I mentioned before, and I also think we need to get more people involved. So just bringing these two worlds together. If there's nothing else that you get from my talk today, I want you to remember that all this cool maker stuff isn't just a lot of fun and neat. It actually has a lot of serious applications. And we really, I think if we can bring these two worlds together, we can make a lot more progress, and we can have more creativity, and we can just tackle bigger problems than we can currently. The makers are having an impact. You know, scientists are smart people. People in my field, there's lots of smart people, but they're not necessarily engineers. They don't necessarily have a background in electronics. Some of them can program pretty well, some of them can't. Those technical skills oftentimes just aren't there. They're not that well developed. But I do see in some cases these two worlds coming together. So with some of the work I've done and colleagues I work with, and also other people who I don't know. And Science is the most prestigious journal perhaps in science, and we're talking about building research equipment with free open source hardware, looking at building lab equipment with 3D printers, for example. So these worlds are coming together. I think it's just starting to happen. I think there's a huge amount of potential to continue to bring those worlds together. So I want to talk specifically about one of my interests, and that's electronic data logging. So just what do we need? What are we trying to get out there? What are the parameters of these tools? So we need something that's configurable, something we can write programs for, right? Which often means we need some sort of computer, microcontroller, or other chip. We need to interface with sensors, and so sensors are actually what is interfacing with the environment, and we're able to understand those signals and bring them into a form that's meaningful to us as scientists. Those signals are sometimes analog signals, in other cases they're smart sensors, digital signals that we can bring the information in without having to do correlations with other things. And I'll get a little more into this later on. We need to keep track of time, so we need a real-time clock. We need to transmit or store information, typically onto maybe some sort of media, like an SD card. When I've talked to people about this work, almost everyone says, well, do you have wireless communication? Do you have wireless communication? And I actually have never gotten into wireless communication myself. I know some people have. One of the reasons is a lot of the places where I work are, 40 miles down a country road and then 18 miles down a gravel road. There's no one to communicate with. And so oftentimes what we'll do is just store on-site, we'll go and download. And we need to visit those sensors from time to time. Anyway, we've had cases where a bear has torn apart an enclosure and chewed on a battery. I don't know why, but you have to get out there from time to time and check it and make sure your equipment is still working as you had imagined it would. We need a power supply. We need some sort of protection from the environment, so some type of enclosure. I'm in Olympia, Washington. It rains about 55 inches a year there. We work in the mountains where it might rain 80 inches a year. It's a very wet environment. But it's not that hard, really, to keep things working. So I work with Arduino, and Arduino is an incredible platform. It's not that well equipped for data logging right out of the box. There's poor power management. If any of you have worked on an Arduino project, the batteries will die very quickly. There's limited memory. You can store stuff in non-volatile memory on the chip, but it's very limited. There's no real-time clock, so we don't really know when a measurement was made, and we often need to know that information. And then it has limited analog resolution. And so just, you think of a measurement, and just the amount of precision you can get is limited by Arduino. We can make an Arduino platform work. We can buy shields. We can build onto it. Early on, I decided that's not the route I wanted to go. It's a lot of work. It's a lot of extra money. You don't get to optimize perhaps the way you want. You go with existing parts. And so I'll talk about my development path that addresses this question of electronic data logging. So replication is difficult. Arduino's easy, but not that easy. And people who have a background in computer science or engineering, Arduino is too easy. It's just so easy. It's funny, being around makers, you assume everyone in the world knows about Arduino. You get outside that community and people have no idea what you're talking about. And so even though it's easy, it's not that easy. I don't have an expectation that I'm going to give somebody an Arduino shield and a board and they're going to make it work. Some people for sure, but again, there's a huge number of people out there who can benefit from this technology, and I think this many people are. There's some hurdles there. I think if we can lower some of those hurdles, we can get more people involved. So the project I've been working on, after a brainstorming session, we said we'd call it the SODA project. Simple, open data acquisition, so just easy to use data loggers. That's our goal. This was the first iteration. We started working with Arduino for maybe a year, and I decided let's break out of the Arduino box. We're still using the same chips. We're using that development environment, and again, it's an incredible platform. And one of the things that's great about it is we have the capability of doing these things. Let's just start over again on the hardware side and build our own hardware that's configurable for our particular purposes. Pretty quickly, you realize, okay, we're not going to get this easy replication part down by building stuff on perf board. My partner and I think this is just another interesting part of this whole maker community. Neither of us are electrical engineers. We don't have a background in this type of stuff per se. We like to hack. We both have a lot of energy and wanted to build stuff. And I think I'm old enough to really think it's incredible that people without this kind of background, who aren't specialists, who aren't spending a ton of money, can really build stuff. It's just amazing to me. It's very exciting, and it's one of the things that motivates me to try to sort of spread the gospel. Anyway, next iteration is let's design and build boards, PCBs, and then we'll populate them. And we built some of these boards and put those out, and that lowered again the bar to making things easier. We can build lots of them. We can put them out in the field. But as we moved on, we found we wanted more. We went to it with an SD card, and really just following the trail other people have laid down. A lot of these things have been developed already. We're just trying to customize them for our purposes. And this is our current iteration, and this is our SODA high efficiency board. It has all the parts I was talking about before. Let's skip that one. Anyway, so we're using one of the Arduino chips, the 32U4 chip. We have developed a circuit that has very, very low power consumption. Oops. All right, low power consumption, high precision analog digital converter, so we can measure things like thermocouples and strain gauges. A highly accurate real-time clock, a micro SD card, which basically means we can save as much data as we want. So really, my message is here that it doesn't take much. The maker community has really opened up all these doors. These things are possible. We're working with our hardware. We're developing an easier interface in terms of a Arduino library to try to get people who might be afraid to dig in to just use Arduino the way we might use some of these other commercial data loggers, because I think there's a lot of people that can get over that hurdle. And something like our board is going to cost maybe a tenth or less of a commercial data logger. And this is really exciting to me. Science runs on data. We need to collect more data. We have all these questions about the environment and climate, and we just need to have a huge amount of data flowing in to people who know how to analyze it. And I'll talk more on that as well. So sensors, sensors are like our sensors are our eyes, ears, skin, and nose. So just like we're sensing things, they're physical devices that go out and somehow take something that's happening in the real world and bring it into something that we can record with the computer. All right, maybe I won't even bother with the slides anymore. Anyway, there's lots of sensors out there. It's, I think, a really fun exercise to say, hey, I wonder how I can measure this. I talked about measuring tree growth. How can we measure tree growth? Well, you don't do it the way you would do it if you were a person. We have diameter tapes we wrap around trees. You have an electronic sensor that takes some sort of signal that correlates with tree growth. Soil moisture sensors, humidity sensors. This is really kind of a fun exercise to think, What are the things that are important to us as scientists? How do we view the climate? How do we sense that electronically? And then from there, it's pretty easy to store it and then go ahead and process this data. Lots of people are making their own sensors. I think that's a really neat other aspect of the maker community. What are some questions we would be able to answer or things we could understand better if we can only measure them? It's really, science is a lot about measurement. If we can measure it, we can start to make sense of it. So enclosures, we worry a lot about rain. Animals are important too. I learned in my day job as a serious scientist to always wash your hands before handling cables and so forth. It helps to reduce the amount of incidences where animals will chew through your cables. It's amazing what rodents will chew through. You can also, if you continue to have problems, there's different types of conduit you might put wires through for sensors. I often use snapware, things like you put spaghetti in after dinner, and it has a nice firm lid. I'll drill a hole in it. Here's a sensor. It's actually one of our versions of those dendrometers used to measure tree growth. This is just in a neighborhood. It's a snapware attached to a fence. The hole at the bottom is on the bottom where the wires come out. Very rainy place, and this data logger survived fine in that environment. We've had cases where you open up the box and it has become an ant nest, and so we found mothballs are effective in keeping insects out of your enclosures. So I'm going to talking about my work. We'll talk a little bit about one of my colleagues' work, who works for ARS, Agricultural Resource Services, in Mississippi. I guess I put Missouri, MS, I meant MI. Or did I mean MS? Anyway. So I just thought this was neat. He's working independently. He's doing a whole very similar using Arduino-based data logging. He actually is using wireless sensors because they're working in test fields where they have the ability to transmit information to dedicated packages to log data. One thing I thought was funny when he sent me these pictures was he has a XB radio to transmit data, but it's inside a turkey baster on top of one of his poles here. And really, it's brilliant, right? It's about the right shape. It's about the right size. We know it's waterproof. I thought that was cool. The pole is a bike pole from a kid's bike. You know, you don't want tractors to run over your sensors. You need to be able to find them. Those things are really, really tough. You can't break them. And they have a flag attached already. So that was pretty cool. And his enclosure, he's using an Arduino-compatible board. He basically is building the kind of system I built, but piece by piece. And that's the payload that's both the XB radio and the microcontroller. Just one other, the unmanned aerial vehicles are awesome and neat, and they're finding applications as well. I threw the slide together from another group that I interact with in Olympia, Washington, who's looking at doing aerial surveys in a natural resources environment with unmanned aerial vehicles. Of course, at this point, it's only a hobby because of regulations, but certainly at some point, this is also going to be important. And really, again, in science, we run on data, and if we can get more data, we can have more sophisticated views of how the world works. So I think it's exciting. All these pieces coming together. I'll talk just quickly. You know, I wanted to say something about statistics, and it's a very exciting field too. Not as exciting as putting parts together, but there's an open source community in statistics. Something that's really, I think, it has a lot of the same energy as what you find here. Probably not as many kids playing around with stats as playing around with Arduinos. But really, that's where you gain insight. That's how you communicate your results, oftentimes in science through statistics. And statistics really are your reality check. And in other words, when you see something, we form an opinion, but that doesn't carry much weight. Seeing something once doesn't carry much weight. Seeing something similar again starts to carry weight. This is what statistics is all about. Bringing all these observations together and say, how much weight do we have? How certain can we be that what we think is true based on all this observation? So if nothing else, I wanted to just mention, I use a package called R. It's a statistical language. It's open source, lots of libraries. I don't know if we'll make any converts today, but statistics are exciting. It's really where the rubber hits the road. R has also developed, RStudio, which is one of the R IDEs, has developed a product called Shiny, and that's a product to share graphs, statistics summaries with people. And the bottom line is these tools are accessible. Anyone can use them. It doesn't take a lot of money. We still need to know what's going on. We can't just work blindly. So it does take work. It takes knowledge in order to formulate hypotheses and understand data. But these tools are there. Somebody with that much money, somebody in a country that doesn't support science the way the United States does, can have access to these tools. And I just wanted to make people aware of that. And so that's it for me. I might have a minute or two if for questions. Yeah. On my board, it's 18 bits. Yes. 10 on an Arduino board, yeah. The question was how many bits on the ADC on the board that we've designed. It's an 18-bit ADC versus a 10-bit on an Arduino board. Any other questions? Yeah. Yes. That's the kind of thing you don't know until you start watching. And it's basically has to do with water balance. They expand at night, and then they start contracting during the day. And I can go on and on. Trees have mechanisms to shut down how much water they lose, and you can even see that point in the afternoon, and they'll quit shrinking quite so fast.
What's the measurement tool around the tree instead of the personal?
Right. So that one was a strain gauge. I use a point dendrometer, so it's basically just a potentiometer that bolts into the tree. So, and as the tree pushes out, it pushes it out. And we get similar results. The question was, how do you measure a tree growth? And the commercial version used a strain gauge, so it has a very small change in resistance as this thing flexes, and we're using a potentiometer. Also uses a change in resistance. It's a much bigger signal, though, per unit of change. Well, thanks a lot. I'll be around if anyone has additional questions.